Turkey's fifth-generation fighter jet program, KAAN, is now entering a crucial phase in its development. The Turkish defense industry has begun accelerating the assembly and testing of several new prototypes simultaneously. This technology is crucial because it helps improve the aircraft's maneuverability while reducing its radar signature. Before the assembly process begins, engineers create digital designs using computer-aided design technology. All aircraft components are visualized in 3D models so that every detail can be checked from the outset. This technology allows manufacturers to identify potential errors before physical production begins. One of the key characteristics of the next-generation fighter jet is the use of lightweight yet strong composite materials. These materials typically consist of carbon fiber combined with special resins. Their advantage is that they are lighter than ordinary metals but offer very high strength. Composite panels are produced in a special chamber with controlled temperature and humidity. Technicians use automated machines to cut and shape sheets of material according to the digital design. The material is then placed in an autoclave, a high-pressure oven that hardens the composite structure. The next stage is the assembly of the aircraft's main components, such as the fuselage, wings, and tail. In modern production lines, this process is carried out using robotics with a very high degree of accuracy. The fuselage, or body of the aircraft, is usually divided into several large modules. Each module is assembled separately before finally being assembled on the main line. Automated robots help ensure the precise positioning of each panel to the micron level. Even the slightest error can affect the aircraft's aerodynamic performance. The latest generation of fighter jets has a much more complex structure than previous generations. The engine is the heart of a modern fighter jet. The latest generation typically uses a turbofan engine with supercruise capability, meaning it can fly supersonic without afterburners for extended periods. Engine installation is carried out with great care, involving the fuel system, while cooling, electronic controls, and high-pressure air ducts. The new generation of engines also features a full-authority digital engine control FADIC system. This technology allows the computer to automatically regulate engine performance, optimizing efficiency and thrust under various flight conditions. Furthermore, some of the latest fighter jets are beginning to use thrust vectoring technology, which allows the engine's jet direction to be changed to enhance extreme maneuverability. One of the most critical components of the next generation of fighter jets is the avionics and radar systems. Modern aircraft are now equipped with AESA, active electronically scanned array radars capable of tracking multiple targets simultaneously with high accuracy. On the assembly line, the radar is installed in the nose of the aircraft, along with infrared sensors, optical cameras, and electronic warfare systems. All of these devices are connected via a high-speed internal computer. Network.sensor fusion technology is a key feature of the latest generation. The computer system will combine data from various sensors and present simpler information to the pilot. This will enable the pilot to make faster decisions during combat. Future fighter jets are also designed to connect with companion combat drones. Therefore, a high-speed data communication system is a critical component of the assembly process. The cockpit of a modern fighter jet is significantly different from that of older generations. Nearly all instruments now use high-resolution digital touchscreens. Pilots are also assisted by a smart helmet that displays information directly on the visor. During the cockpit assembly stage, technicians install a fly-by-wire flight control system that replaces the conventional cable mechanism. All pilot commands are translated into computer-controlled electronic signals. Artificial intelligence technology is also being implemented to help pilots analyze threats, select weapons, and determine the best path during air combat. Once all major components are installed, the aircraft enters the internal systems testing phase. Thousands of cables and sensors are individually inspected using automated equipment. The hydraulic system is tested to ensure the wing controls, landing gear, and rudder surfaces operate smoothly. Meanwhile, the electrical system is checked to ensure all radar, computer, and communication devices are operating smoothly. This testing is crucial because modern fighter jets contain millions of lines of software code that control nearly all aircraft functions. Next-generation fighter jets use a special radar-absorbent paint coating. The painting is carried out in a sterile room using automated spray technology to maintain consistent coating thickness. This coating helps reduce the reflection of enemy radar waves, making the aircraft more difficult to detect. In addition to its stealth function, the special paint also protects the aircraft's fuselage from extreme temperatures and corrosion. Before its maiden flight, the aircraft undergoes engine testing on the ground. The engines are run at various power levels to ensure all systems are functioning properly. Taxi tests, or movement tests, are then conducted on the runway. Test pilots check the braking system, rudder control, and engine response while the aircraft is moving at high speed. This stage is one of the most tense moments on the production line because it determines the aircraft's readiness for its maiden flight. The maiden flight is a major milestone in the fighter jet production process. Test pilots check aerodynamic, performance, stability, radar capabilities, and weapon systems. Flight data is sent in real time to the control center for analysis by engineers. If any problems are found, the aircraft is returned to the hangar for refinement. The assembly of next-generation fighter jets demonstrates how modern technology is transforming the global defense industry. The integration of artificial intelligence, robotics, composite materials, and digital systems is making fighter aircraft increasingly sophisticated and complex. Major powers are now racing to develop next-generation aircraft that not only excel in speed and weaponry, but are also capable of operating as modern air command centers. Future fighter jets are even predicted to be able to work alongside autonomous drones in a single integrated combat network. Modern assembly lines are at the heart of all this innovation. This is where thousands of advanced technologies are combined into a single aerial war machine designed to meet future challenges. With continued technological advancement, the next generation of fighter jets will likely possess capabilities far surpassing those of today's fighters. The next generation fighter jet assembly line symbolizes the technological advancement of the aerospace industry. Modern factories are now filled with precision robots, artificial intelligence systems, and digital tools based on 3D simulations that help engineers ensure every component is perfectly assembled. Instead of relying solely on human labor, the production process is now integrated with digital technology.